Okay, so if I were to ask you for like a basic definition of a functional group, do you think you could give one? Like, what is a functional group? Oh, it's a group of atoms that's not carbon and hydrogen anymore. It's, I don't know, chlorine, or today we're going to do an oxygen, hydrogen. It's a group of atoms that kind of takes the place of where normally a hydrogen goes. Does that make sense? Normally a nice saturated molecule is all filled nice up with hydrogens everywhere, right? A functional group basically says remove one of the hydrogens and put something else there. And that something else is a very unique defining characteristic of the molecule. If it has this particular functional group, that's what dictates its properties more than anything else. And so a molecule that has one bromine and has 7 carbons is going to be very similar to a molecule that has one bromine and has 11 carbons, or a molecule that has one bromine and 12 carbons. Does that make sense? If you had 12 carbons and one bromine, and 12 carbons and what we're going to do today, the alcohol group, those will be different. So really the carbon length is really not nearly as relevant as what sort of special groups you can attach to them. Does that make sense? So Monday we did basically the halogens functional group, which essentially means take a hydrogen, rip it off, put a bromine in its place. Why does that work?
As one realizes by carbon.
Yeah, at its core, that's the bonding theory, right? So you've got a couple of carbons in a row, and I don't really care how many there are, so I'll just kind of put like a dot, dot, dot. Like, I don't care how many you have in a row, right? And normally you'd have nice, full, saturated hydrogens everywhere. And what we've decided to do here is rip off the hydrogen, but because bromine, iodide, chlorine, all of those guys, because they all have one bonding electron, essentially it just attaches. Perfect, just like a hydrogen does. Does that make sense? How does it change the properties of the molecule when I throw on one of those guys? That's what I was hoping for. Good catch. Yeah, it makes it polar. Right? Because if you normally have a hydrogen sitting right here, it's nice and balanced, nice and symmetrical. This makes it polar, which changes a few things. One, it's going to up its boiling point. So it's, rather than being like, say, a low boiling point gas or liquid, it's going to have a higher boiling point because it sticks together better. The other thing is it changes its solubility. Polar things are soluble, at least more soluble in water. The more polar the molecule is, the more likely it is to dissolve in water. Yesterday, you guys might have been able to notice this a little bit. When you were combining the cyclohexene and the bromine, did anybody notice there was a little bit of like yellow liquid kind of sitting towards the bottom for a little bit? That was probably due to the bromine and the cyclohexene having slightly different solubilities, and it didn't quite dissolve yet. Does that make sense? It hadn't fully reacted. Eventually, all of the yellow reacted, and therefore was gone. But up until the point where it actually chemically reacted, it actually had to separate itself into 2 different layers based on its polarity. We're actually going to see that when we do our esters lab next week, Tuesday, where it's like almost like the oil and water. You'll have a layer of water, you'll have a layer of oil on top, and you'll be able to see the 2 different layers separate, and that's based on solubility. One of the questions that I have on your assignment, I believe, asks for chemical and physical properties that you can use to separate compounds. One of them would be separating based on boiling point, but another one would be separating based on solubility. If you have 2 things that have vastly different solubilities with each other, they'll separate into layers. You should just be able to scoop the top layer off, almost like I don't know, scooping leaves off the top of the backyard swimming pool. Okay, let's talk about today's topic then. I get off topic, don't I? You have the same sort of molecule. So, nice saturated molecule. And you have this open spot right here where you wanted to attach a bromine or a hydrogen. Well, today we're going to attach a very common functional group called an alcohol. And here's how it works. It involves an oxygen, which has this electron configuration. So unlike bromine, which just has that 1 extra electron, oxygen has 2 extra bonding electrons. So one of them attaches right here. Does that make sense? Well, it means that oxygen has to keep going. Now, there's a lot of different ways that oxygen can keep going. Sometimes it can keep going and attach to more carbons. That's called an ether, and we don't actually cover that in this course. But for what we're going to do today, we're just going to attach an extra hydrogen to the end and kind of finish off the molecule. And this is known as an alcohol. Wait, first question I gotta answer then, because everyone asks, how is this related to booze? That's what alcohol. Okay. Booze alcohol is one type of the large branch of alcohol, but not all of the alcohols that we talk about are the type of alcohols that you would want to drink. In fact, very few of them you would ever want to drink. Does that make sense? Booze alcohol is usually ethanol, and usually it's like diluted considerably. Like typical beer or something like that might be 5-6% weight by volume. Something stronger might be, say, 40 proof or 40%. We use in the lab, like when we're going to use alcohols on Tuesday, we're going to use 100% stuff. And like you'd never drink that. That's way too, well, concentrate, I guess is the right word to use, but like, yeah, it's not been diluted. So, anyways, booze alcohol is one small subset of the large category. Sorry. Some people, they look at this molecule and they think, hey, OH. OH means they think it's a base. That's not true. Anybody know why? Why does OH not mean a base, even though for the last 2 years I've taught you OH means a base?
Is it because it doesn't dissociate?
That's the key. It has to dissociate in order for it to be a base. For a hydroxide to end up being a base, it needs to be something more like NaOH, because then it can dissociate into Na plus and OH negative, and that's what makes it a base. Not the OH on the end of the molecule, but an OH that has dissociated itself from the rest of the molecule. Well, here's a common one you should know its name of. CH3OH. You know its name? Methanol. Yeah, that's methanol. Yeah. Well, does methanol have the ability to turn into CH3 plus and OH negative? And what I would have taught you back in grade 11 at some point is you'd have to ask yourself the question, is CH3 plus kind of a logical polyatomic sort of thing? And you'd say, well, no, I don't think CH3 plus is something that we've ever learned how to name. So based on that, that's not how this works. This bonds covalently. So, yeah, those are the two things I wanted to start with. What an alcohol really works like, and no, it's not a base. So, let's do some examples. Let's skip the word slides. Those are boring. Let's talk about how to make them. That came out wrong. Let's talk about how to make alcohol. Moonshine here. To make an alcohol, it's actually an addition reaction. Take a double bonded molecule. Here's some sort of molecule that's got a double bond in it. We've talked about R before, right? I've talked to most of you guys about how R works. R just refers to like, there's some more carbons going on both sides of this molecule. I don't know how many more. There could be 7 more carbons in each direction. There could be 1 more carbon. Like we don't really care. But take some sort of double bonded molecule, add water. Well, what's water made of? H and OH. Put the H in one location, put the OH in the other location, and now you have yourself this little alcohol functional group. That makes sense? Go ahead. I should go back to this slide. I want to use the right word from now on, because I've been calling it an alcohol functional group. Although it does make an alcohol, the official term for it is called a hydroxyl. It's called a hydroxyl. Does that slide make intuitive sense? Like you can look at that and go, hey, look, yeah, that totally makes sense as to how you'd make an alcohol. So, let's do some examples of naming, and I'm just going to skip the word slides and just go right to one for you. But you guys can read those words later. Name it like you normally do. First, find out how many carbons can you find in a row. So like on this one here, it looks like I can find 4 in a row, right? So I think let's just keep it simple. Here's 4 in a row. 4 makes it bute. And normally you'd call it butane. You'd also hopefully recognize that there is a branch right here. I don't think we'd call this thing a functional group because that's not how it works. I mean, it is something attached to the main chain, but this is a branch. So we'd call that a methyl. Butane. So far, so good? then the question is, well, how do I deal with this hydroxyl group? This is a hydroxyl. So the way we name hydroxyls is you actually work with these at the end of the molecule. Take off the last letter, E, take off butane, and make it butanol. Kind of like methanol, ethanol, and an alcohol with OL, and with all. Does that make sense? Okay, but just like with what we've done otherwise, we still have to tell you where the alcohol group happens to be. And so in terms of what you guys are going to get tested on, you're only going to get one functional group or the other, or double bonds. So like they're not going to give you a double bond and a hydroxyl and some bromines, and later on they'll throw on some other things. Does that make sense? Like you get one or the other. So the way it works for us then is the thing that takes priority is the functional group. So if you have a bond, that takes priority. If you have a functional group at the end of the molecule, that takes priority. So we need to give this the lowest number possible, which I believe would be attached to number 2. So we would call a butan-2-ol. We also need to number the methyl as well, though. So this is a 3-methyl butan-2-ol. That makes sense? Okay. That's the way I need to show you to do things on the diploma. You may see this written in another way. You might also see this written as a 3-methyl 2-butanol. This is how I originally learned how to name things. Can you guys see how they've just slightly tweaked where they put the number? Rather than putting the number in the middle of the word, which is what we're going to do, I've also learned how to do it where you take the number and you throw the number just right in front of the word. And that implies that whatever suffix you have, it's in the 2 location. So when I go buy chemicals, I have to, in my mind, just remember that if I'm looking for a butan-2-ol, to put the 2 in front. So when you guys do our lab next week, Tuesday, and you look for, like, say, a propan-2-ol, I'll write that out, prop-and-2-ol, if you're looking for something like this, when I actually have it labeled, it's going to be called a 2-propanol. I mean, it's kind of the same thing. Does that make sense? Okay. What else do we got here? A whole lot of words. Sure. Here, why don't you guys try drawing these then? Could you draw me methanol? Why is there a number attached to it? There's only one carbon in methanol, right? So in methanol, you would need carbon, and it looks like you just need an OH group in one of these locations. Ooh, I should point something out here. This O right here technically has lone pairs on it. We don't usually draw the lone pairs, but it may be worthwhile for you to recognize that they still do exist. But normally we don't worry about drawing the lone pairs. That's usually not that important to us. Does it really matter which hydrogen you put the OH group on? Well, no, you just rotate the molecule otherwise. Ethanol, B. Well, does it really matter which carbon you put it on? I think either way, it's the number 1 carbon, right? So you could draw the OH group going sideways. You could draw it like going downwards if you want. I don't really think it makes a difference. So there's ethanol. One propanol, or propan-1-ol. Well, you need 3 in a row. But now it actually matters which carbon you put the alcohol group on, right? The one place you cannot attach it is the middle guy. What would you call it if it was on the middle one? Propan-2-ol, or 2-propanol, whichever one you use. So H, 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 H. I'll throw it on the top this time. Again, it doesn't really matter. And just because I'm getting a little tired of drawing all these carbons out, here's the other way you could draw it. 1, 2, 3, 4. All right, I'll draw it like with sticks instead. And then I have to indicate that off of the number 1 side we have an alcohol. So it doesn't really matter whether I go from the left or the right-hand side, but over here I'm going to draw an OH. Now this looks at first blush like a pent, because you'd think you have 1, 2, 3, 4. You might think that that's a 5th carbon, but if the little line is pointing to somebody else, then it's not a carbon there. Does that make sense? So you could just draw it like 1, 2, 3, 4 like that, and then have this guy go to an OH, and that makes it a 1-butanol. If you wanted a 2-butanol, then you'd draw it like that. Does that make sense? Cool. Okay. Naming and drawing is probably not your biggest challenge. Right? I mean, once you learn how to add a new functional group, it's like, okay, just tell me the new rule and I've got it. That makes sense. So what you're probably going to need to spend more time focusing on is some of the properties. So let me go back to some of the slides I skipped. All those wordy slides. Try to find the key information we needed there. I really don't go through my notes very well anymore, do I? Okay, what's useful here? This is what we need to talk about here. These things can hydrogen bond. Okay, so it's been a while since some of you have done bonding. I need to do a quick recap about how a hydrogen bond works, in case you've forgotten. Does anybody remember how a hydrogen bond works? Okay, so who is capable of forming a hydrogen bond? Oxygen can, yeah. If you have oxygen attached to hydrogen in a bond, that'll work. There's actually 2 others plus 1 more, sometimes 1. Not carbon. Nitrogen will work. What was that? Well, it has to be someone attached to hydrogen. Fluorine, yeah, fluorine's the most electronegative. Those are the 3 that definitely hydrogen bond. The other one is chlorine to hydrogen. These things are capable of hydrogen bonding. Okay, let's talk about why. It's like a fight. I think I use the example normally of sleeping in bed with my wife, and she and I are fighting for the covers. Does that make sense? And Melissa takes the blanket and she rolls over in the middle of the night and rips all the covers off of me because we're sharing the covers, but like, is it really an equal sharing sort of thing here? Only in name. Does that analogy make sense? And what's happened here is in the fight for electrons, hydrogen is about a 2.2 on electronegativity scale. Fluorine, I believe, is 4.0. Fluorine shares, I don't know if that's the right word to use. Like, fluorine steals those electrons pretty much entirely. So if I were to come in, or is it locked? Let me grab that door. If I were to draw where the electrons happen to be, they're almost entirely over there on the fluorines. Hello. Oh, you're in luck.
Thank you.
Yeah, no worries. Where was I? Fluorine essentially entirely has these electrons. What that does is it makes fluorine like the negative end of an atom, and it makes hydrogen very positive. Now, this is very unique to hydrogen, though. What is hydrogen made of? 1 proton, 1 electron. What happens if you steal its 1 electron? Well, all that's left is hydrogen is a proton. This is essentially a single proton. And that proton can bond to any lone pairs sitting somewhere. Well, the cool thing about fluorine is that fluorine is going to have some lone pairs. So if you have a second molecule just like this positive hydrogen can attach itself to that lone pair on the fluorine. So the only things that we know about that do this are fluorine, oxygen, nitrogen, and chlorine. I didn't talk about this probably when we did your bonding unit, but fluorine and hydrogen are the kinds of molecules, fluorine and chlorine are the kinds of molecules where the molecule would have to stop. It would be self-contained. You could not keep building on one side and the other. However, oxygen actually has the ability to keep going in the other direction some more. And so does nitrogen. Nitrogen could keep going in the other direction if you wanted to. So we need to keep our eyes open when we get asked questions about boiling points and hydrogen bonds for things that have this ability, because hydrogen bonds have very high boiling points. That's essentially what happens to it. Monday, I guess, I mentioned that we were going to start making a bit of like a ranking system for boiling points. Maybe you can start making a chart somewhere. Boy, I need to make more room here. If I were to give you something that's just looking like this, this will have the lowest boiling point. Just some basic old-fashioned, nothing special about a hydrocarbon. Pretty low boiling point. If I were to give you the exact same size molecule, but now throw on, like, say, a bromine, that's going to increase its boiling point. Why? What's that? It's polar, yeah. And due to its polarity, it means that there's like a positive negative side of the molecule that can stick together. We sometimes say like partially negative and partially positive, but due to this thing's ability to be polar, it's a little higher on the list. You're going to want to save some room in between, but if you were to do the exact same molecule and attach an OH group at the top, that's pretty much the top of the list. Okay. If you had a similar length carbon chain and you threw the hydroxyl group at the top, that has the highest boiling point. Why? Well, one, it's polar, but two, more importantly, it has that hydrogen bond capacity, because hydrogen is bonded to oxygen. And I mentioned a few minutes ago, there are lone pairs on oxygen. We don't normally draw them, but that makes a difference because, yeah, this molecule will stick together. As we do our other functional groups, they're going to fit kind of in the middle here. But one of the things you're going to need to be able to do, though, is rank and compare boiling points. In fact, I want to think that's one of your assignment questions. Let me see if I can find that real quick. Where am I looking here? Open. If you guys have your assignments nearby, can you find number 4? There you go. Okay, so number 4 basically gives you a table of 3 different molecules. One is a cyclobutane, one is a propan-1-ol, and one is a pentan-1-ol. And part B basically says, compare the boiling points and tell me why they're different. So let's start with the first one, cyclobutane. What's special about cyclobutane? No, that's about it. Not a whole lot. Sorry, cyclobutane, I don't mean to insult you, but like you have nothing special on you, right? There's no functional groups. So what should happen with its boiling point? It should be really low, right? There's no reason for one cyclobutane to stick to the next one, other than marginal London forces. Does that make sense? Now compare the next one, propan-1-ol. Well, the first one had 4 carbons. The next one's down to 3 carbons. Normally, you'd think that means less boiling point. But look, its boiling point's now nearly the same thing as water. It's up to 100 degrees Celsius. Why? Well, because it's an alcohol. Alcohol's way at the top of our list for boiling point, because it can hydrogen bond. Well, then compare it to the one right below that, pentan-1-ol. Well, the only difference between those two is one of them has 3 carbons and then a hydroxyl group. The other one has 5 carbons and a hydroxyl group. Well, the one that has more carbons, slightly bigger. Bigger means a little more London force, so that's why it's a little bit higher in boiling point. Does that make sense? Part C says compare the solubility. Why does cyclobutane have no solubility in water? Because it's not polar. And due to its non-polarness, it has no ability to dissolve in water because water's polar. Polar things will dissolve other polar things. Cyclobutane is not polar. It has nothing special about it to give it a pull on one side. It's just a whole bunch of carbons and hydrogens, and they balance each other out. That makes sense? But looking at the next two, propan-ol and pentanol and propanol, they have high solubilities because they are polar. They can hydrogen bond. So therefore, water can dissolve those ones. Does that make sense? Okay, cool. I just answered number 4 for you. I mean, not all of it, but you need to elaborate on it. Okay, back to this. Where did I leave off? Because I'm kind of jumping around everywhere. Well, I think that's what we need there. This slide here just reminds you need to give the lowest number to the hydroxyl group, but I think I've already mentioned that a few times. So, done this. This just goes through some notes there. Oh, okay. Let's do this now. I have never seen a diploma question on this, by the way, but I wouldn't be doing my job thoroughly if I didn't point this out, just in case they questioned you on this. So there's actually 3 different types of alcohols. We call them primaries, secondaries, and tertiaries. And it may be easiest for me to explain these ones based on just showing you examples first. So here are 3 different alcohols. This one will be called a primary alcohol. This one's a secondary alcohol. This one is called a tertiary alcohol. You want to take a stab at figuring out why they're labeled suchly?
Depending on if they're on the first, second, third.
Pretty much. Here is a carbon. How many carbons does this carbon attach to? And I would say it attaches to 1 carbon. And therefore, this alcohol right here is a primary alcohol. Here is a carbon right here. How many carbons does it attach to? 1, 2 carbons. Therefore, this alcohol right here is a secondary alcohol. Does that make sense? Now, Justin, your definition was pretty good, but it's not based on whether it's on the first, second, or third. It's based on how many it attaches to. So although this was on the first carbon and this was on the second carbon, this one right here is not technically on the third carbon, actually. But here's a carbon. How many carbons is it attached to? 1, 2, 3. Does that make sense? That's why this guy right here is called a tertiary alcohol. Why can't you have a fourthiary alcohol? There you go. That's a great example. I heard what you said mostly. So yeah, there'd be no room for the OH group, right? If you had a carbon going this way, this way, this way, and this way, hang on, you need to have a hydroxyl group as well for it to be an alcohol. So if that comes up, which I've never seen it before, but if it comes up, that's the definition of primary, secondary, tertiary. Yeah, so here's the definition. Primary alcohol, the OH group is bonded to 1 other carbon atom. Like the carbon atom carrying the OH goes to 1. The carbon atom carrying the OH goes to 2 or it goes to 3. So. Okay, why don't you guys try one here? So I've been talking for a while. Try naming this thing. And I guess after you name it, just so that you can figure out whether it's primary, secondary, or tertiary. You could probably do that in like 30 seconds. No, it shouldn't take you 30 seconds. It should take you 2 seconds. Figure out whether it's primary, secondary, or tertiary. How many carbons in a row? 5. By the way, we don't cover alcohols and double bonds. So like it's gonna have to have only single bonds. Otherwise that really screws things up. So this is gonna make it a pent-ane-all. And the naming scheme you guys need to know is how to put the number in the middle of the name. So it looks like it's off of the number 2 branch right here. There is also a 2-methyl. This is a 2-methyl pentan 2-all. You may see this called a 2-methyl 2-pentanol as well. You might see it written like that. I think the second method might be a little bit nicer for saying, because it sure is awkward to say pentan 2-all, like that sentence. Instead, it sounds kind of stilted. But the top method is the one that you have to name on the diploma. So, primary, secondary, tertiary. Yeah, tertiary. Is that obvious to everybody? Awesome. Okay, let's move on. Okay, try this one. Alright, so you got 4 in a row. Butane. Looks like the alcohol is off of the number 2 branch. 1, 2, 3, 4. So it's a butane 2-ol, or a 2-butanol. And then you've got 2 methyls. So it's a 2,3-methyl butane 2-ol. Good, you caught my mistake. Dimethyl. Good catch. Alright, you guys seem to have the hang of it. Okay, sometimes we actually can have polyalcohols. Maybe you've heard of glycerol before. This would actually involve having, like, say, 3 alcohols on the same molecule. This is something that you would be expected to be able to handle. The only difference is then you throw, like, tri or di as a prefix before the alcohol. Yeah, you could have tetra. Yeah, you could have tetra. It means it'd have to be like alcohol, 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 alcohol. You could have lots. So here's the one change though. Put the E back on the word. You guys see that? If there's only one alcohol, what we do is we take the E off of the word and you'd make it propan-3-ol. Something like that. But if there's multiples of them, we make it propane-1,2,3-triol. So put the E back on the word if you need a di or a tri. I would be really surprised if somehow you were tested on like the absence or presence of just the one letter E. Like that's pretty mean to test you on that. But okay. Do you guys think you could handle drawing this without going through it? Should we move on? Okay, let me get to elimination reactions then. You could also do this, by the way, with cyclics. So C6H11OH basically means you're going around in a circle and you've ripped off one of your hydrogens, put it on the hydroxide group. Or here's a benzene ring with one of them pulled off. So if you have a benzene ring, you know how sometimes benzene is known as a phenyl group? We'll just call it phenol, that's all. Do we want breakfast? Well, the breakfast card here too. Nobody? We're good. Thanks, guys. Okay, find the slide on elimination reactions. This is the last kind of major part of today's topic I need to focus on. Okay, you should know things like formation, decomposition, single double replacement, combustion. You should also know how to do redox reactions, which involves reduction and oxidation. And then on Monday, I taught you substitution, which basically means rip a hydrogen off, put something else in its place. That takes a while. As you can see from the lab we did, it took until today for most of that orange-yellow solution to finally turn kind of clear. So substitution takes quite a while. You should also know about addition. What sort of molecules can undergo addition reaction?
Non-saturated.
Sure, unsaturated. Non-saturated, yeah. Unsaturated, I think is the word we'd use, yeah. You need a double bond or a triple bond. Today we're going to talk about elimination. And elimination is essentially the opposite of addition. So you know how addition means take a saturated, unsaturated molecule and fit something into that spot? Well, here we're just going to rip something out of its spot and make a double bond. So it's just the opposite. We've actually already learned a word for one of these. It was called cracking, or like dehydrogenation. Here's an example of it. Here's dehydrogenation. Take an ethane molecule, heat it up, add heat, and what you can do is you can break off some hydrogen and make yourself double bonds instead. So hopefully you guys know this word. It was dehydrogenation. Dehydrogening a molecule. Take hydrogen off a molecule. This, we called it cracking. Technically, it's part of the larger umbrella of what's called elimination reactions. Basically, you're ripping something off. Okay. So I want to show you a couple of examples of elimination that fit with alcohols. So again, most of these are pictures. We can do elimination reactions from alcohols, and it's just the opposite of how you make an alcohol. Here, you've got an H and an OH group. Well, what happens if you rip off both the H and the OH? What does it make? It makes water. Makes sense. So it's the exact opposite of how to make an alcohol. To make an alcohol, take a double bonded molecule, add water. It's also possible to do a elimination reaction where you pull off a water. You do need a catalyst, though. I don't even know what the catalyst happens to be. It probably changes based on what it is you're working with. So, we would call this dehydration. Dehydrogenation means pull off hydrogens. Dehydration, I mean, what happens when you're dehydrated? It means you're thirsty, right? You're lacking water. This molecule right here is now lacking water because you pulled off that water. That makes sense? Awesome. Okay. This one is a little more complicated. It's got a pretty cool name, though. It's called dehydrohalogenation. Dehydrohalogenation. Okay, let's just deconstruct that word, dehydro. Yeah, you're kind of doing something with a water. You need to remove a water somehow, but you also have to remove a halogen. Okay. And so there's actually a way, you know how we learned about making our halogenated atoms a while ago? This is how you'd actually take an atom with a chlorine on it, and how you'd make it go back to just a good old-fashioned no chlorine on there. What you do is you take the chloroethane and you add hydroxide. Now, you can't actually add hydroxide just by itself. So what you'd probably do is you'd add sodium hydroxide. And the sodium would be a spectator ion, okay? So add a base. It has to be a base. And what happens here is the OH of the base, it is going to find a way to rip off that hydrogen right there. And that's the dehydration. That's how you're taking off a water. You're taking off this H right here, along with this OH right here, and you're making yourself water. Now, can you just rip off just one of these things right here? Would that make the bonding principles fit? And the answer is, well, no, then you wouldn't have enough bonds. So what happens is, as well, this chlorine will also just kind of fall off. And now what happens in its place is you put a double bond. Does that make sense? Okay, you know how I said you can't just add OH by itself? You have to add NaOH. Well, guess who that Na is going to bond with? Yeah. Which is still a spectator ion, so we often don't bother writing that in there. Now, it doesn't matter whether it's sodium or calcium or lithium or whatever it happens to be, but you have to add some sort of ionic base. The base part of it rips off the hydrogen. The chlorine will fall off too, and it'll attach itself to the other ionic product, essentially. Did that make sense? That's a bit of a more complicated reaction. One of the downsides to this unit is it's mostly memorization. Like, there's no math to it. But if I ask you what dehydrogenation is, if I ask you what elimination is, if I ask you what hydrocracking is, if I ask you what fractional distillation is, you got to have a fairly good memory to kind of know all these different processes and terms. So, this one's pretty unique. Dehydrohalogenation is quite the word to it. So, okay, let's try an example here. I want for you guys to write a structural formula for the preparation of butene from 2-chlorobutane. We're going to try to write this reaction here. So let's start with 2-chlorobutane. What would a 2-chlorobutane look like? Well, butane would be 4 in a row. And on the second one, whichever side we start going from, on the second one we need a chlorine. So I'll do it that way. And I'm actually going to go through and write out all the hydrogens this time, just so hopefully we can see them all. Okay, we're going to add a strong base. Sodium hydroxide will work. Is it the sodium we care about? No, it's the hydroxide, right? Because what's going to happen is this hydroxide will pull off, say, this hydrogen right here. And in doing so, it'll make you water. The chlorine will also fall off and attach itself to the sodium, so you'll also have sodium chloride. We could, if we wanted to, remove the sodiums. Those are spectator ions. What's the remaining byproduct? What's the remaining organic thing? Well, it looks like it would be 1, 2, 3, 4 in a row. We ripped out these two right here, so the double bond would go right there. How do we name this thing? What do we call that? But-2-ene. Does that make sense? Okay.
I have a question.
Yeah, go ahead.
So how did you put it on the one? So I know you double bonded, but how did you know to put it on that one?
Actually, that was going to be the next question I had here. I think you're seeing something that I was going to try to allude to next. How did I choose for it to be this hydrogen right here? Okay. Oh, yeah, I guess that's a good point here, because it said we're making butene. Let's say that we were doing the reaction and we didn't know what to expect, though. It is entirely possible that this hydrogen right here comes instead. Does that make sense? Let's say that, I'll write this out a second time here. Let's say that this chlorine right here and this hydrogen, let's say it wasn't those ones that ended up getting ripped off. Let's say that it was this chlorine and this hydrogen that got ripped off. Does that make sense? Well, then what would it make? It would still make your water and your sodium chloride, but now your double bond would actually be in this location right here, which would be a but-1-ene. We've talked about this a little bit before. When you do organic reactions, sometimes you have more than one reaction happening simultaneously. This, like if we added 2-chlorobutane to sodium hydroxide, it would make this and it would make this. And I don't see any reason why it wouldn't be about a 50% split for both, just based on the probability. Because, I mean, it could take this one or it could take this one. Right? Like the probability looks about the same either way. How would you separate out the 2-butene then? What sort of property would you use? Well, you can do solubility. But this one right here is probably polar or nonpolar? Does it have a functional group? Is there any reason for this molecule to be particularly like lopsided? Okay, so I say this molecule is not nonpolar. What about this one? It's also probably nonpolar. So will solubility really separate these two molecules from each other? I'd say no. What else can you use to separate molecules? Boiling point. Yeah, that's how you separate them. Right? Ideally, one of these would have a slightly different boiling point than the other one. Right? I mean, you might be talking one boils at 60 and the other one boils at 63. That makes sense. So then set the temperature to 61.5. Right? That's how you separate them. Does that answer what your question was, Dakota?
Yeah.
Okay. So the only reason I need to do this one here is because it said we were making butene. But you should recognize that when you do a lot of chemical reactions, often you make... how many of you started the post-lab questions on your lab? Because one of them was like, show me how to create isomers. These would be isomers of each other. You can also do multiple products as well, where you like rip off one chlorine, then you rip off the next chlorine, then you do the next one. That can be multiple products, but often you actually have multiple reactions happening simultaneously that you can't control. So you need a physical or a chemical way of separating molecules. Does that make sense to everybody? Okay, what else do I have? Oh, we're almost done. Okay, let's do one last slide here. And we'll take a break. Okay, so the elimination of elements of a water molecule from an alcohol. Let's get to what matters here. Write the structural formula equation for the preparation of but-2-ene from butene-2-ol in the presence of a catalyst. Okay, so how do you make butene-2-ol? 4 in a row. On the second one, we need an alcohol. This actually says we're just using a catalyst. I didn't actually figure out what the catalyst was, but we're using some sort of catalyst. So this occurs. How's this going to make but-2-ene then? which hydrogen would you have to rip off? That one right there, yeah. There, right there. We're going to rip off a water molecule. That'll rip off water. And you'll be left with 1 carbon, 2 carbon, 3 carbon, 4 carbons. And right in the middle, you have your double bond. Is that the only reaction that would happen, though? No, it's entirely possible to do just what I described last time. It's entirely possible that you could accidentally have ripped off that water molecule, and that would give you but1ene. How do you separate them? Boiling point. Because I don't imagine their solubility would be that much different than each other. Both of them are nonpolar. So find a boiling point difference. That makes sense? So summary of today's new reaction type.
Susan's back. Can you please call 100?
Elimination basically means take a molecule that has some sort of cool functional group on it and find a way to rip that functional group off of it. Okay? If it's a hydroxyl group due to an alcohol, add a catalyst, rip off the OH and rip off another hydrogen, and you'll have water. If there is a chlorine, bromine, iodide, fluorine, if there's one of those on there, you have to do the dehydrohalogenation, where you have to add a base. If you add a base, the base will rip off the hydrogen for you, and then the chlorine, bromine, iodide, or fluorine will come off as well, and it'll attach itself to the other ionic product, which, like, for us, is sodium. So. Alright, so there's a summary slide. So, quick reminder of the 3 main concepts I want you guys to have. 1, appreciate that there's a lot of organic chem that you can do, right? And really, all we do every day now is I just teach you a new functional group, right? Which leads into the second concept. You got to be able to name and draw molecules. And then last thing, you should know some of the reactions that make them. Does that work? So, tomorrow we're going to do the same thing again, only we're just going to learn a different functional group. Tomorrow's functional group is called the carboxylic acid. And it looks something like this. Carbon attaches to an OH group, but rather than getting to bond to like hydrogens and kind of keep going for forever in this direction, what ends up happening is you don't get both of the hydrogens. We actually take both of those hydrogens off, and we have what's called a carbonyl group, which is a double bonded oxygen there. And so this is called a carboxylic acid. So we'll talk about that one tomorrow. Any questions? All right. Take a break. You guys have just over half an hour to do some stuff. So let me know how I can help otherwise.